Hi, everyone. I'm Philip, a fifth-year PhD student at CMU, advised by Dr. Justine Sherry. I'll be presenting the findings of our Internet Fairness Watchdog, Prudentia. This is joint work with my excellent colleagues at CMU, UCSD, and Hong Kong University. So what exactly do we mean when we say fairness? There are many notions of fairness in the community, and we'll be specifying what exactly we mean with the help of Taylor Swift and her boyfriend, Travis. Now, after a long, hard day of entertaining us on screen, they like to go home and entertain themselves. And they do this the way most of us do, by getting on the internet. For Taylor Swift, this means watching the latest episode of Breaking Bad on Netflix. And for Travis, this means watching his favorite funny cat videos on YouTube. Unfortunately for them, their ISP speed is not fast enough for both of them to be able to watch both videos at the highest quality. So the question then is, what happens? One possible outcome is Taylor Swift ends up with 5 Mbps of the 30 Mbps, which results in very poor video quality, while Travis ends up with 25 Mbps, the lion's share, and gets to watch his cat videos in 4K, which seems pretty unfair. On the other hand, a more fair outcome would be if both of them shared bandwidth equally. And that's the kind of notion of fairness that our fairness watchdog tries to measure. Specifically, we run various services against each other, and we look at how fairly they share their throughput. In addition to this, we also look at QoE degradation for services like real-time video communication and also web page load times. So now that we know what fairness is, why do we want to build a service fairness watchdog in the first place? The first reason is that internet services today are actually too complex to effectively model. And this is because internet service behavior is a combination of CCA behavior and application behavior. So application level control loops like ABR for video algorithms. And both of these components have been getting increasingly complex over the last several years, which means the only effective way to understand services is to measure them, not model them. Second, congestion control today is being developed as a live service. This means that there are updates constantly being pushed to congestion control algorithms, which can change their fairness properties. And we observe this ourselves with the deployment of BBRv3 changing the fairness properties of many Google services. So clearly, it doesn't make sense to do a one and done measurement for fairness anymore. Our fairness measurements need to be live and continuous. So it's important to have a live watchdog. Lastly, while the companies we talk to were extremely interested in making sure that their services aren't unfair, at the end of the day, there is very little inherent incentive structures within a company for them to invest heavily in fairness. Put simply, no one gets a promotion for helping competitors do better. And as a result, a third-party independent watchdog is the ideal entity to fulfill this burden. And we hope that Prudentia serves as a watchdog that can highlight instances of unfairness to both service owners and the community for greater scrutiny. So what has our watchdog seen so far? The first is that unfairness is actually present on today's internet amongst popular internet services. And in the worst case, the losing service ends up with just 16% of its fair share of throughput. We find that fairness needs to be measured by service developers and not just CCA developers, because CCA do not tell us the entire story of service behavior. We find that fairness evaluation needs to be continuous because both service and even kernel updates can actually change fairness properties. And lastly, we find that fairness is idiosyncratic. And a lot of the extreme unfairness that we see is actually due to very specific interactions between very specific services. And we find that bandwidth can also have an effect on fairness. So for the rest of the talk, we're first going to talk about the methodology that Prudentia uses to make its measurements, the results we get from this methodology, and lastly, some lessons for testing that we derive from Prudentia's findings. So how does Prudentia do what it does? At the core of our testbed is a controlled bottleneck that we use to set various network conditions to evaluate internet service performance on. So what this looks like is we run two services, say Netflix and YouTube, over a shared bottleneck link using a software switch. The software switch we use is called BESS, and this is what lets us set various network conditions like bottleneck bandwidths or RTTs and queue sizes. And finally, the content is consumed by two Mac Mini clients running automated instances of Chrome to maximize the experience to maximize the similarity to the experience a real user would have. So the specific network conditions we test are two. The first is the moderately constrained setting, which has a bottleneck bandwidth of 50 Mbps. This corresponds to the median bandwidth experienced by the 50th percentile of countries, according to speedtest.net's global speed index. And then we have the highly constrained setting, which is 8 Mbps, which corresponds to the median bandwidth experienced by the bottom 10 percentile of countries today. And we run from a single vantage point, and it's well known that RTTs can play a big role in fairness. So to eliminate the effect of having a limited vantage point, we normalize all RTTs of flows in our testbed to 50 milliseconds. And we use a queue size of approximately 4 PDP. And at any given point in time, we select two services out of all of these to measure fairness for. And one interesting note is that anytime in this talk, if I say anything along the lines of the fairness when the service competes against Neurino, Cubic, or BVR, I'm referring to their fairness when they're competing with an iPerf instance doing a bulk transfer with one of these CCAs. So let's look at the results. And we're going to look at the results in two stages. First, we're going to look at throughput fairness, and then we're going to look at QoE degradation. So what does throughput fairness look like under contention? So we first need to understand exactly how we measure fairness. And the fairness threshold we use is not Jane's fairness index, which is a very popular fairness metric. Instead, we use maximum fair share because this allows us to account for application limited services too. So what I mean is, let's consider a 50 Mbps bottleneck link. And let's say Google Drive and YouTube are competing over it. Google Drive can utilize the entire link, so it can go up to 50 Mbps. YouTube can just use 14 Mbps. So a fair share between them would really be Google Drive getting 36 Mbps and YouTube getting 14 Mbps of that link. The maximum fraction fair share would tell us that this split is 100% fair. But JFI would tell us it's only 0.84, which is less than 1, which means it's not fair. So clearly, MMF is more appropriate. As an example, what an unfair scenario would look like is if Google Drive got more than its fair share of bandwidth. In this case, its MMF is more than 100%, which is 119%. And in the case of YouTube, it's getting half its fair share, so its MMF is 50%. So yeah, more than 100 is fair, less than 100, not fair. Let's take a look at what fairness in general looks like today. On average, we find the losing service obtains just 72% of its fair share of throughput. And in the worst case, the losing service can end up with just 16% of its fair share. And lastly, the most unfair service we measure is Mega, while the least unfair service we measure is YouTube. This is just a quick glimpse at all the fairness outcomes. I would encourage you to take a look at the paper if you really want to understand what this graph means. But this just at a glance tells you what fairness looks like today on the internet. But we won't be looking at it for the sake of time in this talk. So one of our first findings is that the CCA does not tell us the whole story. So what does this mean? We find that the most and least contentious services we measure actually use different versions of the same CCA. So on this graph, on the y-axis, you have the throughput in Mbps. On the x-axis, you have the incumbent service. That's the service whose throughput we are measuring on the y-axis. And the yellow bar indicates the throughput that this service gets when competing against Mega. And the orange bar is the throughput this service gets when competing against YouTube. And here we can already see that when Google Drive competes against Mega, it gets clearly less than its fair share, or close to 2 Mbps. But when competing against YouTube, it ends up getting more than its fair share. And we can see this trend continues amongst most services in general, where they do fare badly against Mega, but end up getting more than their fair share against YouTube. And these experiments were in the highly constrained 8 Mbps setting. The next instance is that the most extreme cases of unfairness that we see on the internet today are actually due to multi-flow services. And anyone who's worked in congestion control fairness knows that if you're going to use multiple flows, you're automatically going to get a larger fraction of the link. But what surprised us was the fact that multi-flow services are actually prevalent on the internet today. So both Netflix and Mega, which is the fourth most popular file hosting service in North America, use between 4 and 5 flows to transfer data. And as one might expect, this results in very unfair outcomes for competing services. So this is a graph of the throughput obtained by various services on the x-axis when competing against Netflix and Mega. Clearly, it's less than their fair share in general, with one notable exception, which is when BVR services compete against Netflix. This is not particularly surprising because Netflix is using a variant of Neurino, and past work has shown that a single BVR flow can hold its own against multiple Neurino flows. Lastly, we find that unfairness and underutilization can actually both happen at the same time. So what this means is, for example, when Neutrino and Cubic compete with Mega, they experience extreme unfairness and get just 20% of their fair share. But at the same time, link utilization itself is less than 83%. So that means not only are these services experiencing unfairness, there's actually 17% of the link bandwidth that's simply being wasted and not being used by either service. So in summary, what all of these findings are pointing us towards is that while the internet has evaluations have traditionally focused on evaluating CCA performance, especially in the context of fairness, maybe it's time we started evaluating service performance instead. Because clearly, just knowing the CCAs that these services used would not have predicted any of these outcomes that we just saw. And this is just a small subset of the many findings we have in our paper. I would encourage you to take a look at the paper if you're interested in reading more about this. Next, let's take a look at QoE degradation. First, we take a look at how RTC affects how latency affects RTC traffic when competing against various different services. So on the y-axis, we see the packets with RTT greater than 190 milliseconds that's experienced by Google Meet or Teams. So this is the fraction of packets whose RTT exceeds 190 milliseconds. 190 milliseconds is the IQ threshold for comfortable RTC communication. And so the more packets you have with greater than 190 milliseconds RTT, the worse your latency is going to be. And clearly, we can see that when both Google Meet and Teams compete against loss-based services like Neutrino, Cubic, or OneDrive, which is using a variant of Cubic, they end up with a large fraction of packets having very high latency. It actually, these services do not experience any high latency packets when competing against delay-based services like BBR or application-limited services like video traffic in the moderately constrained setting. One notable exception is Mega, which uses multiple BBR flows, still surprisingly causes a large fraction of packets to experience higher latencies for both Google Meet and Teams. The next is we find that web page load times themselves can actually increase by 3x under contention. So on the y-axis here, you have the web page load time, and on the x-axis, you're going to see different websites. Right now, we're just looking at youtube.com, and the load, and it takes 7.7 seconds to load when running by itself with no competing traffic. But on the other hand, when we introduce competing traffic, this web page load time can increase all the way up to 21 seconds. And right now, when I say web page load time, we're referring to the time it takes for the YouTube homepage to load, not a specific video. And we see that this extends even into the moderately constrained setting, where you think there's plenty of bandwidth to go around. YouTube's page load times can almost double in the worst case. And this trend remains true for the other websites we measured to varying extents. All to say that even web browsing activity that we consider innocuous, like loading a website, is itself not immune to the effects of contention. So with this, let's talk about some of the lessons for testing that we gained from the findings that Prudentia gave us. And one of them is that we should be really evaluating fairness continuously, and not just because of service updates like changes to the quick stack or CCA updates, but even simple kernel upgrades can change the fairness properties of your service. So here on the y-axis, you have the throughput in Mbps. On the x-axis, you have different incumbent services. Right now, we're looking at just YouTube. And we can see that when YouTube was competing against iPerf running BBR as present in Linux kernel version 4.15, YouTube ends up with close to its fair share of throughput. But when competing against BBR in Linux version kernel 5.15, we see that YouTube actually gets close to just half its fair share. On the other hand, when Dropbox and Google Drive compete with Linux kernel version 5.15 BBR, they actually experience an increase in throughput. So not only do fairness properties change, it's often not even possible to predict which direction it's going to change in for all services. Lastly, we find that fairness is quite idiosyncratic. And what we mean by this is that a lot of fairness outcomes can be due to interactions between very specific services. For example, Cubic is fair to most services it competes against, but causes Neutrino to get only 20% of its fair share. Along a similar vein, we find that fairness is actually not transitive. What this means is that you can have a service A that can be unfair to service B, a service B that's unfair to service C. But service A can end up being completely fair to service C. And we have specific examples of this in the paper if you'd like to take a closer look. And we also find that fairness can be idiosyncratic with respect to even the bottleneck bandwidth. Here, we're going to look at the throughput that YouTube obtains when competing against Dropbox. And going into this, our team had two competing hypotheses. One was that as the bottleneck bandwidth increases, YouTube's throughput share is going to keep increasing too, simply because there's more bandwidth to go around. Another hypothesis was that when it's competing against Dropbox, which uses BBR v1, the multiplicative probing nature of BBR might result in the probing becoming more aggressive at higher bandwidths. And as a result, YouTube might get less throughput at higher bottleneck bandwidths. What we see is actually both. We see that when YouTube, as we increase the bottleneck bandwidth, YouTube's throughput first increases, then decreases, and then finally increases all the way up to 12 Mbps, which is the throughput, maximum throughput it could obtain at the time. So clearly, both assumptions were wrong or right, depending on how you want to look at it. And the conclusion from all of this is that we should be testing all passive services for fairness and in a variety of network settings. So in conclusion, we saw today that unfairness amongst popular services does exist on today's internet, and as low as 16% of the fair share is obtained by the losing service. We saw that fairness needs to be measured at the service level and not just at the CCA level, because these two can differ quite greatly. And we also found that fairness values need to be continuous because both service and kernel updates can actually change fairness properties. And lastly, we found that fairness should be tested across all passive services in a variety of network settings because fairness is clearly idiosyncratic. And lastly, the overall recommendation Prudentia presents is that we should perform continuous exhaustive pairwise testing in common network settings for fairness. Prudentia was and is intended to be a community resource, so you can actually look at all of our results on internetfairness.net. If at any point in this talk you felt like you'd like to dig deeper into some particular result, you can go as far as downloading PCAP for individual experiments from this website. So please do check it out. And thank you.